You are drifting through empty space at 99.9% the speed of light. And the light ahead of you is still pulling away at exactly the same speed it always was. No matter how much energy you pour into the engine, no matter how close you climb, that gap never closes. The beam does not slow down for you. It does not notice you at all. In 1887, two physicists in Cleveland aimed a beam of light in every direction the Earth travels and found that its speed never changed, not by a single metre per second. That one result broke a century of physics. It told us that time itself slows down for anything that moves, that space contracts in their direction of travel, that the energy required to reach the speed of light is not just enormous, it is infinite, and that this speed is not merely fast. It is the rate at which causality itself moves through the universe, the absolute boundary between what can influence what. For more than 100 years, no experiment, no particle, and no signal of any kind has ever crossed that boundary. Then, at the turn of the 21st century, two independent teams studying the light of dying stars confirmed what cosmologists had quietly suspected for decades. Space itself is expanding, and beyond a certain distance, it is carrying galaxies apart faster than light will ever travel. The speed limit holds for everything inside the universe, but the universe itself has never obeyed it. Tonight, we trace the centuries of discovery that reveal this limit, explore the physics that makes it unbreakable, and confront the one thing in nature that has already found a way around it. If you are new here, subscribe. It is the simplest way to join us for what comes next. This is the story of the fastest thing there is, and why even that is not fast enough. There is a number at the heart of the universe, and it governs everything. 299,792,458 metres per second. That is the speed of light in a vacuum, and since 1983, it has not been a measurement. It is a definition. The metre itself is now defined as the distance light covers in 299,792,458th of a second. We stopped measuring the speed of light and started measuring everything else against it. But this number does not belong to light. That is perhaps the most important thing to understand before we go any further. Light travels at this speed because it has no mass, and anything without mass is compelled by the architecture of space-time to move at precisely this rate. Not slightly below, not fractionally above, but exactly at it. Gravitational waves travel at the same speed. So do gluons, the particles responsible for binding quarks together inside the nucleus of every atom. If a photon was somehow given even the faintest whisper of mass, it would slow down, but the speed limit itself would not move. It would remain right where it has always been, indifferent to what reaches it. This is not a speed limit in the way most people think of one. It is not a barrier that something fast eventually hits. It is a property of space-time itself, a boundary built into the geometry of the universe, and one that cannot be approached the way a car approaches a wall. As any object with mass accelerates toward this speed, something strange begins to happen. Time, for that object, starts to slow down. Distances ahead of it begin to compress. The energy needed to push it even marginally faster climbs on a curve that steepens with every fraction of a percent gained, rising not towards some very large number, but toward infinity. At the speed of light itself, the equations do not just become difficult, they collapse. Time ceases to pass. Length shrinks to nothing. The energy required becomes limitless. No amount of fuel, no conceivable engine, and no trick of engineering can close that final gap. The restriction is not technological, it is structural. It is the shape of the space you are trying to move through. And what makes this limit truly extraordinary is not just its strictness, it is its reach. This speed is not merely the fastest rate at which light can travel, it is the fastest rate at which anything in the universe can influence anything else. A cause here, an effect there, and between them, an absolute ceiling on how quickly the one can produce the other. Physicists call it the speed of causality. It governs the propagation of forces, the transmission of information, the connection between events separated in space. Every fundamental interaction in the known universe, electromagnetic, gravitational, nuclear, respects this boundary. Nothing crosses it, and yet something does seem to cross it. On the largest scales the universe has to offer, galaxies are receding from one another at velocities that exceed the speed of light. Not because they are flying through space at impossible speeds, but because the space between them is expanding, stretching silently and continuously, carrying everything within it apart. Beyond a certain distance, that expansion adds up to recession faster than any photon could ever hope to cross. The speed limit holds for every object, every particle, every signal moving through the cosmos, but the cosmos itself is under no such obligation. The stage obeys different rules than the actors upon it. How that is possible, how the most absolute law in physics can coexist with a universe that appears to disregard it, is what this story is about. But to understand the answer, we first need to understand how we discovered the speed of light in the first place. Because for most of recorded history, the very idea that light moved at all was considered absurd. The dominant view, argued most forcefully by the French philosopher René Descartes in the early 17th century, was that light was instantaneous. It departed its source and arrived at its destination in the same moment, regardless of distance. There was no speed to measure because there was no travel to observe. Galileo challenged this sometime around 1638 by attempting to time a flash of lantern light bounced between two hilltops. The experiment was elegant in principle but hopeless in practice. The delay, if it existed, was far too brief for human reflexes to catch. Galileo could only conclude that light was either instantaneous or extraordinarily fast. The question remained open. It took a completely different scale of distance and a moon orbiting another planet to settle it. In 1672, a young Danish astronomer named Ole Rømer arrived at the Royal Observatory in Paris to work under Giovanni Cassini, then one of the most respected astronomers in Europe. His task was careful, repetitive, and unremarkable. He was recording the precise times at which Io, the innermost of Jupiter's 4 great moons, disappeared behind the giant planet and emerged again on the other side. Io completes an orbit roughly every 42.5 hours, and by tracking hundreds of these eclipses over months, Rømer was building tables intended to improve celestial navigation. What the tables revealed, however, was a pattern that Io's orbit could not explain. When Earth, in its own journey around the Sun, was drawing closer to Jupiter, the eclipses arrived slightly ahead of schedule. When Earth was pulling away, they came late. The discrepancy was small at first, a matter of seconds, but it grew with distance. Over the full span of Earth's orbit, from its closest approach to Jupiter to its farthest point, the total accumulated delay reached roughly 22 minutes. Romer saw the answer. The eclipses themselves were perfectly regular. What changed was the distance the light had to travel to reach him. When Earth was nearer to Jupiter, the light arrived sooner. When Earth was farther, it arrived later. The 22-minute difference was the time light needed to cross the full diameter of Earth's orbit around the Sun. Cassini, Romer's superior, had flirted with the same idea. On the 22nd of August, 1676, he had told the French Academy that light appeared to take 10 to 11 minutes to travel the distance from the Sun to the Earth. But almost immediately, he retreated. The conclusion was too radical, and the supporting evidence from Jupiter's other moons was less clean. Cassini set the idea aside. Romer did not. On the 21st of November, 1676, he presented his full case to the Academy. The reaction was mixed. Many found it difficult to accept that something as seemingly instantaneous as light could have a measurable travel time at all. But Christian Huygens, the Dutch mathematician and physicist, recognised the weight of what Romer had found. Using the delay and the best contemporary estimate for the size of Earth's orbit, Huygens calculated the speed of light at roughly 220,000 kilometers per second, about 75% of the true value. The number was imprecise because Romer had slightly overestimated the delay, and the orbital diameter was not yet known with certainty, but it was in the right range. Light had a speed, and that speed was finite. Independent confirmation came 53 years later from an entirely different method. In 1729, the English astronomer James Bradley detected a subtle, recurring shift in the apparent positions of stars, a phenomenon he named stellar aberration. The effect arose from the combination of Earth's orbital velocity and the finite speed of incoming starlight, in much the same way that rain, falling straight down in still air, appears to slant when you walk through it. From the magnitude of the aberration, Bradley derived a speed of light accurate to within about 1% of the modern measurement. Isaac Newton had already cited Romer's result in his 1704 work Optics. Bradley's observation removed the last room for doubt. Light moved. It had a speed, and that speed could be pinned down. What no one yet suspected was that this number was far more than a fact about light. It was a fact about the universe, a constant so deeply embedded in the fabric of space and time that it would take 2 more centuries, and the work of a young clerk in a Swiss patent office to begin to grasp just how profound its implications truly were. By the middle of the 19th century, the speed of light was a known quantity, a number that could be measured, refined, and agreed upon. What remained entirely mysterious was what light actually was. It behaved like a wave. It could be reflected, refracted, made to interfere with itself. But a wave of what? Sound is a wave in air. Ocean waves or waves in water. What was light waving through? The answer came from an unexpected direction, not from optics, but from electricity and magnetism. For decades, these two forces had been studied as separate phenomena. Electric charges attracted and repelled one another. Magnets did the same. But a series of careful experiments in the first half of the century had begun to reveal that the two were entangled in ways nobody fully understood. A changing magnetic field could produce an electric current. A moving electric charge could generate a magnetic field. The English experimentalist Michael Faraday had spent years mapping these relationships in his laboratory, demonstrating them with wires, coils, and iron filings. But Faraday was not a mathematician, and the patterns he uncovered resisted formal description. It fell to a Scottish physicist named James Clerk Maxwell, working at King's College London in the early 1860s, to bring those patterns together. Maxwell took the scattered observations of Faraday and others and expressed them as a unified set of mathematical equations. 4 equations that describe the behaviour of electric and magnetic fields and the relationship between them. What emerged was not just a tidier description of known phenomena, it was a prediction. Maxwell's equations showed that when an electric field changes, it creates a magnetic field, and when that magnetic field changes, it creates an electric field in return. The two bootstrap one another, leapfrogging forward through space in a self-sustaining wave. And the speed of that wave was not a free parameter. It was fixed entirely by 2 measurable properties of empty space: the electric permittivity and the magnetic permeability of the vacuum. When Maxwell calculated the resulting speed, the number he obtained was startlingly close to the known speed of light. The coincidence was too precise to be a coincidence. Maxwell drew the conclusion directly. Light is an electromagnetic wave. He was not the first to notice the numerical connection. 9 years earlier, in 1856, the German physicists Wilhelm Weber and Rudolf Kohlrausch had measured the ratio of the electromagnetic and electrostatic units of electric charge, a ratio that, purely from the structure of the units, had the dimensions of a speed. The value they obtained was almost exactly the speed of light. Weber noted the result, but did not pursue its meaning. Maxwell did. He recognized that the match was not accidental, but structural, that the speed of light fell out of the equations governing electromagnetism because light was electromagnetism. The physicist Richard Feynman would later describe Maxwell's unification of electricity, magnetism, and light as the most significant event of the 19th century, more consequential in the long view of history than the American Civil War. Whether or not one agrees with the comparison, the scale of what Maxwell achieved is difficult to overstate. In a single framework, he had explained the nature of light, predicted the existence of electromagnetic waves across a spectrum far beyond the visible, and revealed that 2 seemingly unrelated forces were aspects of a single, deeper phenomenon. Experimental confirmation arrived in 1887 when the German physicist Heinrich Hertz succeeded in generating and detecting electromagnetic waves in his laboratory. Waves that travelled at the speed of light, reflected off surfaces, and interfered with one another exactly as Maxwell's theory predicted. Light was not merely similar to an electromagnetic wave, it was one. But there was something else buried in Maxwell's equations, something most physicists at the time either overlooked or chose not to worry about. The speed that appeared in the mathematics was a constant. It did not depend on the motion of the source. It did not depend on the motion of the observer. It was simply there, fixed and absolute, as if the universe had written a single, non-negotiable speed into the rules governing all electromagnetic phenomena. For a generation raised on Newtonian mechanics, where velocities always depended on who was measuring them, this was deeply strange. Almost nobody noticed. Almost. The physics of the late 19th century rested on an assumption so fundamental that it was rarely even stated aloud. Light, like every other wave, must travel through a medium. Sound needs air. Water waves need water. Electromagnetic waves, the thinking went, must need something too. A substance that filled all of space, was perfectly transparent, and vibrated at the right frequency to carry light from the stars. Physicists called it the luminiferous ether. If the ether existed, and if the Earth was moving through it, then the speed of light should vary depending on which direction you measured it. A beam sent in the direction of Earth's motion should appear to travel slightly slower, carried against the ether wind. A beam sent perpendicular should travel at a different speed still. The difference would be small, proportional to the ratio of Earth's orbital velocity to the speed of light, but with a sensitive enough instrument, it should be detectable. In 1887, 2 American physicists set out to detect it. Albert Michelson, already one of the finest experimental physicists in the world, and Edward Morley, a precise and methodical chemist, built their apparatus in the basement of a dormitory at what is now Case Western Reserve University in Cleveland, Ohio. At the centre of the experiment sat a Michelson interferometer, a device that split a beam of light into 2 perpendicular paths, sent them to mirrors and back, and recombined them. If the 2 beams returned at slightly different speeds, the recombined light would show an interference pattern, a telltale shift in the alignment of the waves. The entire instrument was mounted on a massive slab of sandstone, floated on a pool of liquid mercury to eliminate vibration, and could be rotated smoothly to test every direction. It was sensitive enough to detect speed differences as small as 5,000 meters per second, more than adequate to reveal the effect of Earth's passage through the ether. They found nothing. No shift. No variation. No ether wind. The speed of light was the same in every direction, to the full precision of the instrument. They rotated the apparatus through every angle. They repeated the measurements at different times of day, as the Earth's rotation changed their orientation relative to its orbital path. They returned months later, when the planet had swung to the opposite side of the Sun, and was moving in an entirely different direction through space. The result never changed. The light did not care which way the Earth was moving. It arrived at the same speed regardless. The Michelson-Morley experiment is sometimes called the most famous failed experiment in the history of science. It did not find what it was looking for, and in doing so, it broke something far more important than the ether hypothesis. It broke the assumption that the speed of light behaves like any other speed, that it can be added to or subtracted from depending on the motion of the source or the observer. The null result meant that something was fundamentally wrong with the way physics understood space, time, and motion. The crisis was profound. Maxwell's electromagnetism, the crowning achievement of 19th century physics, predicted a fixed speed of light. Newtonian mechanics, the foundation of everything else, demanded that speeds always be relative. Both theories worked beautifully in their own domains, but they could not both be right. In the years that followed, 2 of Europe's finest theoretical minds attempted to patch the damage. The Dutch physicist Hendrik Lorentz proposed that objects moving through the ether physically contracted in the direction of their motion, shrinking by just the right amount to cancel out the expected shift in the speed of light. It was a clever solution, but it required accepting that the very act of moving through space physically compressed matter in a way that could never be directly observed. because any measuring rod would shrink by the same fraction. The French mathematician Henri Poincaré went further, developing a mathematical framework that preserved the form of Maxwell's equations under changes of reference frame, and introducing the concept of local time. The idea that clocks in different states of motion could tick at different rates. Poincaré even speculated, in a 1904 lecture, that the speed of light might represent an ultimate velocity that nature could never exceed. His mathematics was elegant and, in many respects, remarkably close to the final answer. The equations Lorentz derived would later bear his name and remain in use to this day. But neither man could explain why nature behaved this way. The contraction was a fix, not a physical principle. The local time was a mathematical convenience, not a statement about the nature of time itself. Both were treating the symptoms of a deeper illness they could not yet diagnose. The cure would come from someone who was not trying to save the ether at all, someone who was willing to throw it away entirely and follow the consequences wherever they led. In 1905, Albert Einstein was 26 years old, held no university position, and works 6 days a week as a technical expert at the Swiss Federal Patent Office in Bern. He had clashed with professors, struggled to find academic work, and spent years in obscurity after graduating from the Zurich Polytechnic. He had been thinking about light since he was 16. The thought experiment that haunted him was simple. If a person could travel alongside a beam of light, matching its speed, what would they see? Maxwell's equations implied a frozen stationary wave, but they also forbade such a thing from existing. The beam had to move at exactly the speed of light, regardless of the observer. The contradiction took Einstein nearly a decade to resolve. The breakthrough came in the spring of 1905, shaped by long evening conversations with his closest friend, the engineer Michel Bessot. Einstein would credit Bessot by name in the paper, the only acknowledgement it contained. What they arrived at was not a fix, it was a demolition. On the 30th of June, the journal Annales de Physique received a paper titled On the Electrodynamics of Moving Bodies. It contained no new experimental data. It began with 2 postulates, simple enough to fit on a napkin, and from those alone, it dismantled 2 centuries of assumptions about the nature of space and time. The first, the laws of physics are the same in every inertial frame of reference. No experiment performed in a sealed room moving at constant velocity can reveal whether you are moving or standing still. The second was the revolution. The speed of light in a vacuum is the same for all observers, regardless of their motion or the motion of the source. Not approximately, not after correction, the same, always. This was the step that Lorentz and Poincaré had circled without taking. Poincaré had arrived at mathematics that looked almost identical. He had written the transformations, described the symmetries, even speculated that the speed of light might represent an ultimate velocity. But he never let go of the aether. He treated the constancy of light as a property of the equations, not a truth about the universe. Einstein accepted it as physical reality and asked what reality must look like for it to hold. The answer reshaped everything. If the speed of light is truly the same for all observers, then simultaneity cannot be absolute. 2 events that happen at the same moment for one observer will not appear simultaneous to another moving at a different velocity. This is not an illusion. It is a fact about the geometry of events. From that single insight, everything else followed. A moving clock ticks more slowly than a stationary one, not because it is broken, but because time itself passes at a different rate for objects in relative motion. This is time dilation. A moving ruler is physically shorter in the direction of its travel, not because it is compressed by some force, but because length itself is relative. This is length contraction. Both effects are governed by a single quantity, the Lorentz factor. At everyday speeds, it sits negligibly close to 1. At 90% of the speed of light, it more than doubles. At 99%, it exceeds 7. And as velocity approaches the speed of light, the Lorentz factor does not plateau. It climbs toward infinity. 3 months later, Einstein published a short follow-up asking whether the inertia of a body depends on its energy content. The answer was yes, and the relationship was governed, once again, by the same constant. Energy equals mass times the speed of light squared. A single kilogram of matter, fully converted, contains the energy equivalent of roughly 21 megatons of explosive. The speed of light was no longer merely the speed at which light travels. It was the exchange rate between mass and energy itself. Then, in 1908, the Lithuanian-German mathematician Hermann Minkowski, once Einstein's own teacher at the Zurich Polytechnic, took the framework further. He showed that space and time are not separate things connected by the speed of light. They are a single four-dimensional fabric, space-time. Every object in the universe moves through this fabric at a fixed total rate, the speed of light. Sit still in space, and all of your motion is directed through time. Begin to move through space, and some of that motion diverts away from time. The faster you travel through space, the slower you pass through time. At the speed of light itself, time stops entirely. Minkowski opened the lecture presenting this idea with words that have echoed through physics ever since. Henceforth, space by itself and time by itself are doomed to fade away into mere shadows, and only a kind of union of the two will preserve an independent reality. Einstein initially dismissed the reformulation as unnecessary elegance. He would later call it indispensable. In the span of a single year, from a patent desk in Bern, the understanding of space, time, mass, and energy had been fundamentally rewritten, and threaded through every consequence, appearing in every equation, was the same constant, the speed of light, revealed now not as a property of light, but as the deepest structural limit of the universe itself. A theory is only as strong as the evidence behind it. Special relativity made extraordinary claims about the nature of time, space, and motion, but it also made predictions that could be tested. If time genuinely slows down for objects moving at high speed, if distances truly contract, if the speed of light really cannot be reached by anything with mass, then the effects should be visible. Not in thought experiments, but in measurable physical reality. They are. And they have been confirmed so many times with such extraordinary precision that the constancy of the speed of light and the reality of relativistic effects are among the most thoroughly verified facts in all of science. The most elegant demonstration arrives uninvited from the sky. High-energy particles from deep space, cosmic rays, slam into the upper atmosphere at altitudes of roughly 15 kilometers, producing showers of subatomic debris. Among that debris are muons, heavy cousins of the electron that are created in enormous numbers. Muons are unstable. In their own rest frame, they survive for an average of just 2.2 microseconds before decaying. At the speeds they travel, typically above 99% of the speed of light, that lifetime should carry them roughly 660 meters before they vanish. They should never reach the ground. Most of the 15-kilometer journey from the upper atmosphere to sea level should be far beyond their reach. And yet they arrive at the surface in vast numbers, easily detectable, unmistakably present. The explanation is time dilation, exactly as Einstein predicted. From our perspective on the ground, the muon's internal clock is running slow. Its 2.2 microsecond lifetime is stretched by the Lorentz factor into something far longer, giving it enough time to make the full journey. From the muon's own perspective, it lives exactly as long as it always does. But the distance to the ground is length contracted, compressed into something it can cross before decaying. Both perspectives are equally valid. Both give the same result, and both require that the speed of light is an absolute limit that reshapes time and space around anything approaching it. This was first measured directly in 1940 by Bruno Rossi and David Hall at Echo Lake, Colorado, the first clean experimental confirmation of relativistic time dilation using particles from nature. Decades later, CERN pushed the precision far further. In their muon storage ring, muons were accelerated to a Lorentz factor of 29.3, stretching their lifetime from 2.2 microseconds to 64.4 microseconds. The agreement with Einstein's prediction held to within 0.9 parts per thousand. The theory was not approximately right, it was right. In 1971, Joseph Haefel and Richard Keating carried the test from the subatomic realm into the human one. They loaded 4 cesium atomic clocks onto commercial airliners and flew them around the world, eastward and westward, then compared them with identical clocks that had remained on the ground. The travelling clocks disagreed with the stationary ones by tens of nanoseconds, and the pattern of disagreement matched relativistic predictions precisely. Clocks moving faster ran slower, exactly as special relativity demanded. Clocks at higher altitude, sitting in weaker gravity, ran faster, exactly as general relativity demanded. The effects were tiny, but they were real, and they were exactly where the theory said they would be. The most consequential application of these corrections is one that billions of people rely on every day without knowing it. The global positioning system depends on a constellation of satellites orbiting the Earth at roughly 14,000 kilometers per hour. At that velocity, special relativity causes their onboard clocks to lose approximately 7 microseconds per day relative to clocks on the ground. Simultaneously, because the satellites orbit at an altitude where Earth's gravitational field is weaker, general relativity causes those same clocks to gain roughly 45 microseconds per day. The net effect is a daily drift of about 38 microseconds, a seemingly negligible number until you consider that light travels approximately 11 kilometers in 38 microseconds. Without relativistic corrections applied continuously, GPS positioning would drift by roughly 10 kilometers per day. Every satellite navigation system on Earth, in every phone, every aircraft, every ship, is a functioning test of Einstein's theory, running 24 hours a day. Even the machines physicists use to explore the fundamental structure of matter are themselves monuments to the speed limit. The design of every modern particle accelerator, the bending magnets, the timing of accelerating fields, the shape of the beam pipes, is built on relativistic equations. At CERN, protons are routinely accelerated to 99.9999% of the speed of light. Each orbit around the 27-kilometre ring adds energy, but that energy translates into ever-diminishing gains in speed. The protons are already so close to the limit that their velocity barely changes, even as their energy climbs by orders of magnitude. If the speed limit were not real, if energy did not increasingly resist conversion into velocity as the Lorentz factor climbs, those beams would behave in ways the engineering cannot accommodate. The machines work because the speed limit is real. They would not function for a second if it were not. But knowing that the speed limit exists, and that it has been confirmed beyond serious dispute, is different from understanding why it exists. The evidence shows that nothing with mass has ever reached the speed of light. The question is, what stops it? The most familiar explanation is the energy barrier. As an object accelerates, the energy required to increase its speed grows, not linearly, but on a curve governed by the Lorentz factor. At low speeds, the relationship between energy and velocity is gentle, almost flat. Push harder, go faster. But as the speed climbs past 90% of the speed of light, the curve steepens sharply. At 99%, you need roughly 7 times the rest mass energy of the object just to maintain that velocity. At 99.9%, the factor exceeds 22. And as velocity approaches the speed of light itself, the energy required rises without bound toward infinity. There is not enough energy in the observable universe to accelerate even a single gram of matter to exactly the speed of light. The barrier is not practical, it is absolute. A common misconception is that this happens because the object's mass increases. It does not. What increases is the object's resistance to further acceleration, its inertia. The Lorentz factor amplifies the effective inertia of the object, so that each additional unit of energy produces less and less additional speed. The object does not become heavier, it becomes harder to push. There is a more elegant way to see this. In Newtonian mechanics, velocities add simply, if you are moving at half the speed of light and you throw something forward at half the speed of light, it should travel at the full speed of light. But in special relativity, velocities do not add that way. They combine through a formula built from the geometry of space-time itself, involving quantities physicists call rapidities. The addition law has a remarkable property. No matter how many sublight velocities you combine, the result is always less than the speed of light. You can stack boost upon boost, adding speed upon speed, and the total will approach the limit asymptotically, but never touch it. The speed of light is not a wall you run into. It is a horizon you can never reach, always the same distance ahead, no matter how fast you go. But the deepest reason the speed limit cannot be broken is not about energy or inertia at all. It is about causality. The speed of light is the speed at which cause and effect propagate through the universe. It is the maximum rate at which any event can influence any other event. In the language of Minkowski's spacetime, every event sits at the tip of a light cone, a boundary that divides the universe into 2 regions. Inside the cone lies everything that event can causally reach, every place a signal, a force, or a consequence could travel to within a given time. Outside the cone lies everything that is forever beyond its influence, no matter what. Travelling faster than light would mean crossing outside your own light cone, arriving at a destination before the light from your departure could reach it. And in some reference frames, that would not merely mean travelling very fast. It would mean arriving before you left. Effect before cause. The logical structure of the universe, the very ordering of events that makes physics possible, forbids it. For massless particles, the situation is different. Photons, gluons, and gravitational waves do not approach the speed of light. They exist at it. They have no rest frame. They experience no passage of time. From the moment of their creation to the moment of their absorption, no time elapses for them at all. They do not accelerate to the speed of light. They are born at it, and they cannot travel at any other speed. For them, the speed of light is not a limit, it is the only option. For most of the 20th century, cosmologists assumed the expansion was slowing down. It seemed like the only reasonable possibility. The universe was full of matter, and matter generates gravity, and gravity pulls things together. The expansion that began with the Big Bang should have been decelerating ever since. The only real question was whether it would eventually stop and reverse, collapsing everything back into a single point, or merely coast toward a gentle halt over infinite time. Either way, the universe was breaking. In 1998, two independent teams set out to measure how fast. The technique was the same for both. Type 1a supernovae, the thermonuclear detonation of white dwarf stars that have accumulated too much mass, explode with a remarkably consistent peak brightness. Because their intrinsic luminosity is known, the distance to any individual supernova can be calculated from how dim it appears. And because the light from a distant supernova is redshifted by the expansion of space, the amount of that redshift reveals how fast the universe was expanding when the light was emitted. Compare the two, distance and recession speed, across dozens of supernovae at different epochs, and you can trace how the expansion rate has changed over time. The Supernova Cosmology Project, led by Saul Perlmutter at Lawrence Berkeley National Laboratory, and the High Z Supernova Search Team, led by Brian Schmidt and Adam Rees, worked independently with different telescopes, different datasets, and different analysis methods. They expected to find that distant supernovae were brighter than a uniformly expanding universe would predict. Evidence that the expansion had been faster in the past and was now slowing down. They found the opposite. The distant supernovae were dimmer. They were farther away than they should have been. The expansion of the universe was not decelerating. It was accelerating. The result was so unexpected that both teams initially assumed they had made an error. They had not. When two independent groups, working in competition, arrive at the same unlikely conclusion using different instruments and methods, the conclusion tends to be real. Perlmutter, Schmidt, and Rees shared the 2011 Nobel Prize in Physics for the discovery. What is driving the acceleration remains one of the deepest open questions in all of science. Physicists gave it a name, dark energy, but the name is a placeholder, not an explanation. Whatever it is, it accounts for approximately 68% of the total energy content of the universe. It does not cluster. It does not dilute as space expands. It permeates the vacuum itself, exerting a constant outward pressure that pushes the expansion to accelerate. The simplest theoretical candidate is the cosmological constant, a term Einstein himself added to his field equations in 1917 to prevent the universe from expanding or contracting. When Hubble's observations revealed that the universe was in fact expanding, Einstein reportedly called the cosmological constant his greatest blunder and abandoned it. Nearly 80 years later, it was resurrected. In the current standard model of cosmology, known as lambda CDM, the cosmological constant is the leading explanation for dark energy. But whether it is truly constant, or whether the dark energy is something more exotic that changes over time, no one knows. The implications for the speed of light are stark. The expansion is not merely continuing, it is speeding up. Galaxies that are currently near the edge of the observable universe are being carried away from us faster with each passing moment. The cosmic event horizon, the boundary beyond which light emitted today will never reach us, is not retreating. It is creeping closer. And the disagreement runs deeper still. Measurements of the expansion rate itself do not agree with each other. The Planck satellite's observations of the cosmic microwave background yield a Hubble constant of approximately 67.4 kilometers per second per megaparsec. Local measurements, tracking supernovae and variable stars in the nearby universe, led most prominently by Rees and the Shoes team, consistently yield a value closer to 73. The gap has persisted for years and has only sharpened with better data. It is either a systematic error that no one can find, or a sign that something fundamental about our cosmological model is incomplete. What is not in dispute is where all of this leads. In the far future, hundreds of billions of years from now, the accelerating expansion will carry virtually every galaxy beyond the local group past the cosmic event horizon. Their light will redshift toward infinity and fade from view. A civilization arising in that distant era would look out at a universe that appeared to contain only its own galaxy cluster, surrounded by perfect empty darkness. There would be no evidence that the universe had ever been full of galaxies, no evidence of expansion, no way to reconstruct the cosmological history that we, in our own era, can still read in the sky. The information would not be hidden. It would be gone, carried beyond reach by the expansion of space itself, faster than any signal could ever chase it. Given the absoluteness of the speed limit, it is natural to wonder whether there is any way around it. The history of physics is full of apparent loopholes, phenomena that seem at first glance to violate the restriction. Each one deserves honest examination. The most visually striking is Cherenkov radiation. When a charged particle, typically an electron, travels through a medium like water or glass faster than light travels in that medium, it produces an eerie blue glow, the optical equivalent of a sonic boom. This is real, well documented, and easily observed in the cooling pools of nuclear reactors. But it is not a violation. The speed of light in water is roughly 75% of the speed of light in a vacuum. The particle exceeds the local speed of light in the medium, not the vacuum speed. The universal limit holds. Quantum entanglement is a subtler case. Two particles, prepared in an entangled state, can exhibit correlations that appear instantaneous regardless of the distance between them. Measure the spin of one particle in London, and the outcome of a measurement on its partner in Tokyo is determined at that same instant, not after a delay, not after a signal has passed between them, but immediately. Einstein famously objected to this, calling it spooky action at a distance. But decades of theoretical and experimental work have shown that while the correlations are real, they cannot be used to transmit information. The no communication theorem proves that no signal, no message, and no usable data can travel through entanglement faster than light. The correlation exists, but causality is untouched. Phase velocity offers another apparent exception. In certain materials and wave configurations, the peaks of a wave can travel faster than the speed of light. But the peaks carry no information. They are a pattern, not a signal. The actual speed at which energy and information propagate, the group velocity and signal velocity, never exceeds the vacuum speed of light. The wave may appear to move faster. Nothing meaningful does. The most imaginative attempt to work within the rules while exceeding the limit came in 1994, when the Mexican physicist Miguel Alcubierre published a solution to Einstein's own field equations describing what he called a warp bubble. In Alcubierre's metric, the space ahead of a craft contracts while the space behind it expands. The craft itself never moves faster than light within its own local patch of space-time, but the bubble of distorted space carries it forward at effectively superluminal speed, in much the same way that the expansion of the universe carries galaxies apart faster than light without anything locally violating the limit. The mathematics is valid. The problem is the energy requirement. The Alcubierre metric requires exotic matter, matter with negative energy density, and in quantities that may be physically impossible. The Casimir effect, in which quantum vacuum fluctuations produce a tiny measurable force between uncharged metal plates, is the closest known real-world phenomenon to negative energy. But the effect is vanishingly small, many orders of magnitude short of what a warp drive would require. Harold White at NASA's Eagle Works laboratory explored whether a modified version of the metric might reduce the energy demands to something detectable. The results were inconclusive. The warp drive remains firmly in the realm of theoretical possibility, not engineering. Quantum tunneling is sometimes cited as another candidate. A particle encountering a barrier it classically should not be able to cross can appear on the far side, as though it passed through without traversing the space in between. Some early interpretations suggested the transit was instantaneous, faster than light. More careful analysis has shown that while the timing of tunnelling is genuinely strange and still debated, no information is transmitted superluminally. The speed limit, once again, holds. The pattern is consistent. Every apparent loophole either fails to transmit information faster than light or requires matter and energy that do not exist in any form we have ever observed. The speed of light is not a rule that nature bends when convenient. It is a boundary that everything we have ever tested, built, or imagined has obeyed. There is something misleading about the name we have given this constant. We call it the speed of light, as though light owns it, as though light is the reason it exists. But light does not own the speed of light. Light simply rides it. If photons had mass, even the smallest conceivable mass, they would travel slower. Experiments have placed extraordinary upper limits on the photon mass, and to the best of our measurement, it is exactly zero. But the point is this: if it were not zero, if some future experiment detected even the faintest trace of rest mass in a photon, the speed of light would decrease, and the speed limit of the universe would remain exactly where it is. The limit does not come from light. It comes from the structure of space-time itself. What we call the speed of light is really the speed of causality, the maximum rate at which one event can influence another, the fastest any signal, any force, any piece of information can travel between 2 points in the universe. It appears in the equations governing electromagnetism, but it also appears in the equations of gravity, of nuclear physics, of thermodynamics, of quantum field theory. It connects mass to energy through Einstein's most famous equation. It governs the curvature of space-time in general relativity. It determines the rate at which gravitational waves propagate, the structure of light cones in Minkowski space-time, and the maximum speed at which quantum fields can transmit disturbances. Strip light out of the universe entirely, remove every photon, and the constant remains, unchanged and essential, embedded in the laws that govern everything else. It is not that light is special. It is that this speed is special. Light merely travels at it because it has nothing to slow it down. This reframing is not just philosophical. It changes how we understand the deepest relationship in all of physics, the relationship between space and time. In Minkowski's four-dimensional space-time, space and time are not merely connected. They are aspects of the same thing, measured in different units, convertible from one to the other through a single constant. That constant is the speed of light. 1 second of time is equivalent to 299,792,458 meters of space. Not metaphorically, mathematically. The speed of light is the exchange rate between the two most fundamental dimensions of reality. This is why time slows down for objects moving at high speed. An object moving through space is, in Minkowski's framework, diverting some of its motion away from time. The faster it moves through space, the less it moves through time, because the total rate of motion through space-time, the magnitude of what physicists call the four velocity, is always fixed at the speed of light. Everything in the universe, without exception, is always moving through space-time at this rate. A rock on the ground, a satellite in orbit, a photon crossing the void between galaxies. The only question is how that fixed budget of motion is divided between space and time. Sit perfectly still, and all of your motion is through time. You age, the clock ticks, the world changes around you. Accelerate toward the speed of light, and your motion through time approaches zero. Time does not slow down because of some external braking force. It slows down because there is only so much space-time motion to go around, and you have redirected nearly all of it into space. In 1983, the International System of Measurement formalized what physics had already understood. The metre was redefined. No longer a physical distance marked on a platinum bar in a vault near Paris, but the distance light travels in vacuum in 1/299,792,458th of a second. From that moment onward, the speed of light was no longer something we measured. It was the standard against which all distances were measured. The constant had been promoted from a property of the universe to the foundation of the system we use to describe it. Not everyone believes the constant has always held this value. The physicist João Magejo, working at Imperial College London, proposed a provocative hypothesis known as the variable speed of light model. The idea that in the very earliest moments of the universe, the speed of light may have been enormously higher than it is today. If true, it could resolve one of cosmology's most stubborn puzzles: the horizon problem, the question of why regions of the universe that should never have been in causal contact share the same temperature and density. The standard solution is cosmic inflation, a brief period of exponentially rapid expansion. Mageho's alternative is that light itself was faster, allowing causal contact across distances that seem impossible today. The hypothesis is not mainstream. It has not been confirmed, but it illustrates something important about the constant. Even the most seemingly absolute number in physics is subject to serious, rigorous theoretical challenge. The speed of light may be the hardest boundary we know. That does not mean we have stopped questioning it, and perhaps that is as it should be. A constant this fundamental deserves the scrutiny. We began with a paradox. Nothing can travel faster than light, and yet the universe itself already does. Over the last hour, we have traced the centuries of observation, theory and experiment that reveal this limit and explored why it is so absolute. We have watched it emerge from the timing of eclipses on a distant moon, take shape in the equations of electromagnetism, survive the most precise null result in the history of science, and become the foundation of a new understanding of space and time. We have seen it confirmed by unstable particles raining from the upper atmosphere, by atomic clocks carried around the world on commercial aircraft, and by the faint ripple of colliding neutron stars arriving at Earth in lockstep with the flash of their light. And we have seen the universe work around it, not by breaking the rule, but by expanding the stage on which the rule applies. The expanding universe does not violate relativity, it reveals its full depth. Special relativity says that nothing can move through space faster than light. It says nothing about the behaviour of space itself. General relativity, the deeper, more complete framework, permits space to stretch, to carry galaxies apart at any recession velocity, because the stretching is not motion in the ordinary sense. No object is locally outrunning a photon. No signal is arriving before it was sent. Causality is intact. The speed limit holds in every corner of the cosmos. It is the cosmos itself that is not obliged to stand still. What this means for us, for any civilization bound by the speed of light, is that we live inside a horizon. There is a sphere around us, defined by the expansion of space and the finite speed of light, beyond which we can never send a message, never receive a signal, never know what exists. And that horizon is not static. The accelerating expansion of the universe is drawing it inward, year by year, light year by light year. The portion of the cosmos we can see, touch and influence is shrinking. Not quickly, not on any timescale a human life could notice, but inexorably and without any known way to reverse it. There is a strange beauty in that. The same constant that limits us also connects us. Every beam of starlight that reaches a telescope is a message sent at precisely this speed, crossing distances that would be meaningless without it. Every gravitational wave that flexes the arms of an interferometer is a ripple in the same fabric, travelling at the same rate, carrying the story of events that happened long before we existed. The speed of light is the postal service of the cosmos, infinitely reliable, absolutely impartial, and the only channel any of us will ever have. The speed of light, then, is not a wall. It is the shape of reality itself, the geometry that determines what can be known, what can be reached, and what must remain forever beyond us. The constant was here before the Earth, before the stars, before the first atoms cooled from the plasma of the early universe. It will remain long after the last galaxy has faded beyond the cosmic horizon and the sky has gone dark. It is the fastest thing there is, and the universe is built around it.